Hi, we are going to talk about the t distribution and then running through a one sample t confidence interval for a mean mu. And so this is chapter 10.1 in your book. So chapter 10.1, estimating a population mean. So just as a quick review, this is our formula for a confidence interval for proportions, right? And we use the p hat, the sample proportion value, as our estimate and in our margin of error because we don't know what the population proportion is, right? So we're going to use p hat to estimate p. But here's the thing. When I'm talking about means, if I think about my general formula, I need my point estimate, which is x bar, plus or minus the z star times the standard deviation of the statistic. Well, the standard deviation of the statistic is sigma over root n, the standard deviation of the population over root n. But here's the problem. If I'm sampling, if I don't know what mu is, the population mean, am I going to know what the population standard deviation is? Probably not. So we don't know what mu is. We're trying to estimate it with x bar, and we also don't know what sigma is. So we estimate sigma with s. So you can kind of think of this is like my general formula that you have here. But the problem is I'm using two different statistics, x bar and s, to estimate two different population parameter values, mu and sigma, as opposed to up with proportions where I'm really only estimating the p with the p hat, right? So it's almost like I have another unknown kind of. So again, we're estimating x bar, we're estimating mu with x bar. We're estimating sigma with s. Now, what happens then is that all of my confidence intervals are going to be different lengths. Because remember, my formula was x bar plus or minus z star times s over root n. And in every different sample, every time I take a new sample, which each of these green and red confidence intervals, in other words, each of the like black dots, the black dots is each now an x bar. X bar, x bar. All the black dots are x bars, right? So every time I take a new sample with a different x bar, it's going to also have a different s. And so the s value is going to dictate how long the actual interval is itself. So meaning like this green one, this is the length of the interval, as opposed to, let's zero in on this really short red one here. So what happens if I compare this green one, this green interval, to this red interval? In the green interval, the standard deviation of the sample was a lot bigger than the standard deviation of the sample in the red interval. Now, what's the standard deviation of the population? I don't know, right? That's the whole idea. So who knows which one is better, like a better estimate? I'm not really sure. But the problem is that in this case, we used a 99% confidence level. But if you look at all of these intervals, in a 99%, when I use a 99% confidence level, that should mean that about 99% of my intervals should contain the actual population mean mu. In other words, like this black line, right? But the thing is, they don't. Only 92.5% of our intervals actually captured mu. And that's a big difference between 99% to 92.5. And we did 1,000 intervals. And again, the reason is because my S with each of my interval that I created, my S value is different. So some were shorter and some were longer. And you can see most of the time, look at the red intervals. They're the ones that didn't contain mu. Typically, not all the time, but typically those intervals were shorter, a lot shorter than the other ones. So like, for example, this one, my X bar actually was pretty close to my mu, but my interval itself, in other words, my sample standard deviation was really, really small. Sometimes, like if I look at this red interval that didn't contain the population mean, my X bar was way off, right? My X bar, because of sampling variability, just happened to be really low. So even though my interval was nice and wide, the interval didn't contain the population mean. So, all right, what do we do about it? If we want a 99% confidence level, we need to have a 99% capture rate, right? We need to have 99% of the intervals containing the actual population mean. And so we just said, the problem is most of the time that these intervals are too short. So we need to multiply by a bigger number. We need to make that interval a little bit longer. If we make each of these intervals a little bit longer, not all of them, not all of the red ones are going to then contain mu, but more of them will. Specifically, we need to get it from 92.5 of them containing mu to 99%. All right, so that brings us to what we call a T distribution. So a T distribution is very, very similar to a normal distribution. In fact, when I draw my normal distribution, that's what it looks like. When I draw my T distribution, that's what it looks like. When I draw them, they look exactly the same. I can't really tell the difference. But here's the thing. The T distribution is going to be just a little bit more variable. It's going to have a higher variability than a normal distribution. So let's, in this first paragraph here, it says the critical value T star has the same interpretation of Z star. It's how many standard errors, and remember, we think of the Z being how many standard deviations we are from the mean. We're calling it standard error because we're using X bar and S to approximate. And because I'm using the S value to approximate sigma, it's not a standard deviation, it's a standard error. So anyway, it's how many standard errors we are from the point estimate to get the desired level of confidence. So here's the other thing about T distributions. There's actually not just one T distribution, there's lots. We specify a particular T distribution by giving its degrees of freedom. And degrees of freedom, we've talked about that concept before. Typically, degrees of freedom are related to sample size. Remember, n-1. The bigger the sample size, the bigger the degrees of freedom. But we're going to see eventually sometimes degrees of freedom are related to other things. But in a nutshell, what you need to know is the bigger the things, the bigger the degrees of freedom. Okay? So let's look at this little picture here. So in the picture, the purple is the standard normal curve. So you can kind of see that it's the tallest and the skinniest. It has the least amount of variability. Whereas my T distribution with 2 degrees of freedom, in other words, think of that as a sample size of size 3, is the shortest with the most variability. So it's kind of like the shortest and the fattest. And the T with a bigger sample size, so the T distribution with 9 degrees of freedom, so in other words, the sample size was 10, because 10 minus 1 is 9 degrees of freedom, is kind of in between with the heights and the variability. So what I'm trying to tell you is, the bigger the sample size, the closer, so I'll write this down, the bigger the sample size, and therefore degrees of freedom. So the bigger the sample size, the bigger the degrees of freedom, the closer the T distribution gets to a normal distribution. And as T gets bigger and as degrees of freedom get bigger and bigger and bigger and bigger and really big, your T distribution essentially becomes your normal distribution. All right, so that's a little bit about the T distribution. Let me show you the table, what we call a T table, and you've used this before. This should look familiar. This is from your formula sheet packet. It's also in the back of your book. We call this table B, the T distribution critical values. And we used the bottom of this, oops, zoom in. We used the bottom of this down here with helping us to find Z stars. So remember we said this bottom row here, when the degrees of freedom, look at the top, degrees of freedom, when the degrees of freedom were infinity, these across this row here are our Z stars for a corresponding confidence level. And so now we're going to use the rest of the table, and we're going to use these degrees of freedom down the side to give us confidence levels. So let me show you some examples. All right, so if we want to create a 95% confidence interval using an SRS of size n equals 12. So n equals 12, our degrees of freedom would be 11. So I would go to the table and find on the left-hand side 11 degrees of freedom. And then on the bottom, my confidence level has to be 95%. And then the intersection of that row and that column, my T star would be 2.201. And remember, your T star is pretty much exactly, it has the same interpretation, the same meaning as the Z star, right? Okay. Now, if I wanted a 90% confidence interval from a random sample of 48 observations, so my sample size is 48, my degrees of freedom, would be 47. You're going to notice that the table does not have 47, okay? So the table, after a certain point, it kind of starts going up by like 10. So here's the rule of thumb. You always have to round down. I don't have 47. I either have to choose from 40 or 50. Those are the closest to 47. But to be more cautious, I want like more variability in my T distribution. And remember, the smaller the degrees of freedom, the more variability you have in your T distribution. So this is the T star that you should use. Also, your calculator, remember we did like inverse norm to look up a Z star. Your calculator has this function, the inverse T function. So you could use the calculator as well. Now notice, when your calculator spits out these values, they're negative because you're given like the tail area of 0.025 in a 95% confidence interval. So in a 95% confidence interval, you want 95% in the middle, you want 2.5% in each tail, right? So to find the T star, to cut off the bottom 2.5 and the top 2.5, you would have to type in an area of 0.025. And your calculator spits out a negative value, you can see, but remember a T star, we just always kind of make it negative because in the formula for confidence intervals, we have like plus or minus, which takes care of like the positive T and the negative T. All right. I'm going to show you real fast. I'll pull up my calculator if you want to see where to get that, what menu. So you would go to like second distribution, inverse T. And then, for example, this first one, I would type in the areas 0.025. My degrees of freedom, if my sample size is 12, my degrees of freedom is 11, right? So there you go. One other thing that I wanted to point out is that if you use your calculator, you are able to enter in an exact degrees of freedom. You don't have to round. Remember we said using the table, you had to round down to 40 degrees of freedom. So on the table, my T star was a 1.684. On the calculator, my T star is a 1.678. They're not exactly the same. They will be close. Either one is acceptable. It's fine. It doesn't matter which one you use. You just need to be comfortable using, really, you should be comfortable using both. Okay, let's talk about, now that we know about the t-distribution, let's talk about conditions. So random condition. Remember, we've been saying this all along. If our data is meaningless, so is our confidence interval. If I, if I want to estimate the height of the average person that was sick in high school, but then I only asked the basketball team after school, right? Like I could do everything else correctly, but everything is meaningless because my data didn't come from a good source, right? So we need our random condition. And because I'm going to be doing an SRS, if I sample without replacement, I need to use my 10% condition to be able to use my standard deviation or standard error formula, right? And then the other condition with means was that I needed my distribution of this, my sampling distribution to be approximately normal. Now, in this case, we're saying, even if this condition is met, it's still not good enough to use like a normal distribution, or in other words, like a z-star. And the issue is because of, remember, we have X bar and we have S estimating their corresponding population parameters. So even though we're checking this condition, we still can't use an actual normal distribution, right? Now, how do we check this condition with means? We use the central limit theorem. And if you remember from the central limit theorem, I'll start down here on this third bullet. The central limit theorem says the sampling distribution is approximately normal if the population is normal, or if my sample size is 30 or higher, or if my population distribution has an unknown shape. So I don't know if it's normal, I don't know if it's skewed, and I have a small sample size, so smaller than 30. Here's the new part. Here's what we're going to do. We're going to graph the sample data, and we're going to just take a look at what does the sample look like? What does the shape of the sample distribution look like? Because remember, if we do an SRS, which is one of our conditions, so we've done an SRS. So because I've done an SRS, my sample distribution, meaning like what my sample data looks like, should be very similar to the population distribution. So if my sample data is pretty like, symmetric with no extreme like outliers and crazy stuff going on, I can probably safely assume that my population is as well. On the other hand, if my sample data, if I do like a dot plot of my sample data and it looks like this, if that's my sample and it came from an SRS, probably the population looks similar to that as well. And therefore, I can't say that my sampling distribution is going to be approximately normal. All right, so there's my three conditions. That third condition is the trickiest one to check. So we're going to look at a couple problems to determine if the normal or the large sample condition is met or not. So to estimate the average GPA of students at your school, you randomly select 50 students. Here's a histogram of their GPAs. So do I know about the population, the shape of the population? I don't, but the sample size is 50. So the central limit theorem tells me that regardless of what the population size, shape is, regardless of what the population shape is, if the sample size is bigger than 30, the sampling distribution is going to be approximately normal. So that condition is met. How about this? How much force does it take to pull wood apart? The STEM plot shows the force required to pull a piece of Douglas fir apart for each of the 20 randomly selected pieces. So my sample size is 20. Because my sample size is 20, it's smaller than 30. I don't know anything about the population shape. They didn't tell me anything. So I'm going to look at the sample distribution. Not the sampling distribution, the sample distribution. This is my sample data. Does it look like it's approximately symmetric, approximately normal? Could it be approximately normal? Nope. I have like a strong skew. I probably have some outliers. The sample size is small. So therefore, I should not go any further. This condition isn't met. The sampling distribution for X bar is probably not going to be met. It's probably not going to be close to normal. All right. Suppose you want to estimate the mean SAT math score at a large high school. Here's a box plot of the SAT math scores for a random sample of 20 students. All right, 20, no good. Less than 30 is my sample size, right? They don't tell me anything about the shape of the population, but when I make a dot plot of the sample data, again, I'm sorry, not dot plot, a box and whisker of the sample data, it doesn't look, it definitely has a little bit of a skew to it, but the center, or in other words, the median, is almost like perfectly centered in between the first quartile and the third quartile. And so I don't have like an extreme skew. So because I don't have like an extreme skew, I don't have any outliers, I'm going to say, yeah, the condition is probably met. Now listen, if I had this and then like an outlier or two outliers, then I would probably say, that's probably too much of a skew with the outliers added on as well, so probably no good. So we're not looking for perfection. We don't need perfect symmetry. We just need to be like, yeah, close enough. Okay, so all the conditions need to be met when you're doing a confidence interval and then later on when we're doing a hypothesis test. So you need to check SRS, you need to check the 10% condition, and you need to show a graph if your sample size is small. You'll see what I mean. All right, so confidence intervals, this should look familiar. This is what we've been kind of talking about. Let's jump into, the formula, excuse me. So this is our formula that we kind of reviewed before. We're going to use X bar plus or minus T star, and then the standard deviation from the sample over the square root of n. And our T star comes from the T distribution with n minus 1 degrees of freedom, right? Okay, let's look at an example. So about 73% of American adults claim to have read a book in the previous 12 months. This was based on a 2016 Pew Research Center study that interviewed a random sample of 20 American adults. The same study also reported that the average number of books read by the members of the sample, including those who reported reading no books, was a mean of 12, a sample mean of 12, with a sample standard deviation of 18 books. We want to construct and interpret a 95% confidence interval for the mean number of books read by all Americans in the previous 12 months. So we're going to define our parameter of interest. So in this case, I'm talking about population means. And I should note, one of the most difficult parts of like moving forward, taking the AP exam, taking the mock exam, things like that, is you're really going to have to look at the information given and say, am I talking about proportions? Am I talking about means? So just keep in mind, you know, they're talking about the X bar. They're giving you an X bar. They're giving you a standard deviation. They're asking you to interpret and construct the interval for the mean number of books, right? Okay, so the population mu is the true mean number of books read by all American adults in the previous 12 months. So we are going to do a one sample T interval for mu. T interval because we're using a T star, right? So they told us it was a random sample of 1,520 adults. We checked the 10% condition. And because our sample size is so big, we're going to assume that the sampling distribution for X bar is approximately normal. So I don't have to check a graph or do anything like that. If n is bigger than 30, check, we're good to go. Okay, so what's our formula? X bar plus or minus the T star times the standard deviation that was given divided by the square root of n. Now, let's just quickly review. Our sample size was 1,520. So if I want to go to my table, because to be honest, I actually, it's up to you. You can use the table or the calculator to look up T star, but I a lot of times use the table because I think it's pretty quick and easy. 1,000, remember 1,520 was my sample size. that number of degrees of freedom, 1,519, is definitely not going to be on here, so I should round down. So I'm going to go to the 1,000 line, and I forget, we're doing a 95% confidence interval, so 95% confidence interval, so we're right here. So that should be our T star. Sorry, I can't highlight this for some reason. That 1.962 value, right? So that's where we get that 1.962. Great. Now you need to be able to write this formula down, but just like with proportions, then you're going to go to the calculator to do the actual number crunching. So we're going to go to stat test, and we're doing a T interval. So if I scroll down, I see T interval. Oops. So T interval. And now when you do a T interval, you can either be given raw data, and you'll see what I mean in just a second, or you can be given statistics, like meaning they gave you the X bar, they gave you the S. So I can hit data, and you're going to notice I put data into L1. I don't have that. They give me the X bar, so I'm going to scroll over, hit enter on stats, and I'm going to enter in the X bar that they gave me was 12. Oops, 12. The standard deviation was 18, and the sample size was 1520, right? The confidence level, we want a 95% confidence level. So when I hit calculate, it spits out my confidence interval, and you can see that it matches up with what we have here. So you don't have to do the number crunching. The calculator is going to do it for you, right? You do still need to write this formula. You don't necessarily need to write this part in the middle. I don't care about that part. You need the formula, and you need the interval. Okay. Now we got to interpret it. So we're 95% confident that the interval from 11.09 books to 12.91 books captures the population mean number of books read by all American adults. So remember, our conclusion is always about the population. And now we're talking about means. We're not talking about proportions. Okay. So question B. So in 2011, Pew reported that American adults read an average of 14 books in the previous 12 months. Does your interval from Part A provide convincing evidence that the 2016 mean is different than the 14 books? So again, my interval went from 11.09 to 12.91. 11.09 to 12.91. So 14 is nowhere in that interval. So in other words, I'm saying I'm pretty sure that 14 is not the population mean, right? So there you go. This does provide convincing evidence. Okay. Let's look at another example. And this time, as you can see on your screen already, you're going to be given raw data. You're not going to be given the mean and the standard deviation and all that stuff. So let's read it. A manufacturer of high-resolution video terminals must control the tension on the mesh of fine wires that lies behind the surface of the viewing screen. Too much tension will tear the mesh, too little will allow wrinkles. The tension is measured by an electrical device with output readings in millivolts. Some variation is inherent in the production process. Here are the tension readings from a random sample of 20 screens from a single day's production. Construct and interpret a 90% confidence interval for the mean tension, mu, of all the screens produced on this day. All right, well, in order to do that, I need the sample mean and the sample standard deviation from this data. So I'm gonna type all this data into my calculator, right? Now, let me go to my calculator, stat, edit. So all this data is here in L1 for me, okay? I typed that in before. So I have all my data into, again, stat, edit. I have it all in L1 or whatever list you want. Okay. So construct and interpret a 90% confidence interval. So we want to define our parameter of interest. It's the population mean, mu, tension of all the video terminals produced on this day. We need conditions. We're going to do a one sample T interval for mu. So if you think back, I'll go back. They told us that it was a random sample of 20 screens, right? So they told us it was a random sample, and we're going to assume that 20 screens is less than 10% of all the video terminals produced that day. But now, because N is 20, less than 30, because N is less than 30 specifically, and we aren't ever told anything about the population shape. We need to figure out, well, okay, what do the data tell me? What do the sample data tell me? So I'm going to go back to my calculator, and I'm going to quickly go into second stat plot, and I am going to make some kind of a graph. I'm going to highly encourage you to make a box and whisker plot. Make sure you select the one with outliers. And my data is in L1. My frequency should be at 1. And I'm going to zoom stat or zoom 9 that. So there's my box and whisker. So that's the shape of my sample data. So because my sample, let me go back here. Because my sample data looks pretty symmetric, I don't really have evidence against the sampling distribution being like normal, right? So we're going to say this is kind of close enough. We think the sampling distribution is probably going to be close to normal. All right, so let's talk about like what you actually need to write down. You can see you're going to draw, basically, I'm going to call it like a rough sketch. And when I say a rough sketch of what you see in your calculator, that box and whisker plot, I literally mean a rough sketch. Notice, that's my rough sketch. I don't have labels. I didn't measure things out. I didn't come up with like a number line. It can be a rough, quick sketch. All right? So my conditions are met. Let's move on. So it's a 90% confidence interval. My sample size is 20. My degrees of freedom is 19 and 90% confidence interval, sorry. So 90% confidence interval, 19 degrees of freedom is going to bring me to right here, this 1.729 number, right? So that's my T star, 1.729. So my formula is the mean, which we'll talk about how you can get that in just a second, plus or minus the T star standard deviation over root N. Well, guess what? Good news. We know that we can get the mean and the standard deviation of this data because our data is in L1. We can do one variable statistics, right? We can do one variable statistics of second L1, and it's going to give us the mean of the data and then the standard deviation. And keep in mind, I would be using S, not sigma, because it's sample data. But I actually never actually type one variable statistics. Here's what I do. I go right to stat test, T interval, and if I go over to data, and so I'm selecting data because again, I have my raw data as opposed to like them giving me the X bar 1 and X bar and standard deviation. So my data is in L1, make sure that list is correct. My frequency should still be 1, don't change that. My confidence level, they wanted me to use 90%, so let me make that 90%, and then I hit calculate. So out spits everything I need. So I don't even ever need the one variable statistics because when I do this, it gives me the X bar and it gives me my standard deviation. So it's just like a little bit faster. To be honest, before I write down this formula, I actually use the calculator first and then I go back and write down the formula. Just makes it like one less step, makes it a little easier. Okay, so there's my confidence interval. We need to interpret it. We're 90% confident that the interval from 292.32 to 320.32 millivolts captures the true population mean tension in the entire batch of video terminals produced that specific day. Okay, so again, I just want to reiterate, here's where a lot of people lose credit. We need to check to make sure the sampling distribution is approximately normal. We can easily do that if our N is bigger than 30. If N is bigger than 30, that's an automatic. If n is less than 30, they must either tell you, maybe they'll tell you in the problem that the population distribution is approximately normal. Then we're good, right? But if n is less than 30 and they don't tell you that, you must sketch that graph. All right, let's talk a little bit about margin of error to kind of tie things up. So what affects margin of error? And remember, a confidence interval is always the point estimate, in this case, like x bar, plus or minus the margin of error. So in this case, the margin of error is t star times s over root n. So this is the margin of error, the stuff after the plus or minus. That's what we're talking about. So this should all sound very familiar. Margin of error decreases as sample size increases. Remember, bigger sample size, less sampling variability. So S over root n is your sampling variability. So the bigger sample size, the smaller the margin of error. Again, assuming that everything else remains the same. Our formula for margin of error, T star times S over root n. So the margin of error is proportional to 1 over n. 1 over root n, that should be, 1 over root n. So quadrupling the sample size will cut the margin of error in half. And this was the same as with proportions as well. The margin of error, square root keeps being missing, sorry. The margin of error will be larger for higher confidence levels. So remember, if I want to be really confident about like a prediction about tomorrow's temperature, if I want to be 99% confident, I could say, tomorrow the temperature is going to be somewhere between 0 and 100 degrees, right? Sure, it's not telling me much information. My margin of error is huge, but I could also say my confidence level is probably like 99.999%, right? So bigger margin of error, higher confidence level. And then maybe most importantly, margin of error does not account for bias in the data collection process. In other words, sorry about that, guys. In other words, margin of error doesn't account for bias in the data collection process. If my sample data came from a bad place, voluntary response or whatever, convenience sampling, whatever, everything is meaningless. The margin of error doesn't mean anything, right? All right, that's it. That wraps up section 10.1. Thank you so much for watching. Have a great day.